So as we start with spectroscopy, we're going to start with infrared spectroscopy. So we will be covering, as we said previously, a number of different spectroscopic techniques that will allow us to identify organic molecules. Again, as we said, each technique gives us a certain piece of the picture of the molecule. And again, ultimately what we will try to do is that we will try to be able to use all of these put together in order to identify a molecule. And one of the ways that you'll do that, in addition to, the things that you might expect, practice problems, quizzes, exams, homework, etc., is that our very last lab for Organic 1 is going to be one where literally I hand you a compound and it's your job to go through the lab and try some of the different techniques that you've learned to figure out what it is. So again, you can think of this as very much like doing a puzzle. And each one of these techniques is going to give us different pieces to the puzzle. So infrared, or IR as we'll refer to it, is useful for functional group identification. So in other words, infrared will tell you I have a ketone, I have an aldehyde, I have an alcohol, and it can give you all of that information. What IR won't give you is how those functional groups are put together. So IR will not give you any information about connectivity. All right, so let's just start out by looking at a sample spectrum. And right now we're not going to worry about really anything in this spectrum. But just to look at this as an example. So there's always two pieces of information that we're going to get from each peak. Each peak is going to have a wave number associated with it, and we'll explain in a few minutes what wave numbers mean. In addition to that, each peak will have a percent transmittance. Now notice that this percent transmittance scale goes from 0 at the bottom to 100 at the top. So the lower the transmittance is, the more intense the peak is. Now, from there, we typically divide our IR spectrum up into two regions. And we make that division here at about 1500 wave numbers. So what are the differences in those two regions? Well, on the right side of the spectrum, we have what's known as the fingerprint region. So this is the region of the spectrum below 1500 wave numbers. Now, why do we call it that? Well, in the fingerprint region, it's often way too complicated for us to get much specific information. But the fingerprint, just like we think of with normal fingerprints, is unique for every compound. And so if you're comparing two spectra, if their fingerprint regions match, then you know you're dealing with the same compound. But outside of that, the region that we normally concern ourselves with is the higher part of the region, so from 1500 up to about 4000. That's where we get our functional groups. And when we're looking for functional groups, there are three things that we want to look at for a peak, and they all mean something. So first and most important is the position, or the wave numbers of the peak. Second thing is how strong or how intense is the peak. So a peak that is very, very strong means a lot different than a peak that's much, much weaker. And finally, what about the shape of the peak? So the shape of the peak will also tell us some things about the functional group that's present. Now, you may have noticed as we've been talking about, the scale that we see at the bottom is wave numbers. Now, that's a unit that at this point is probably not familiar to you. And we use this symbol here to represent wave numbers. So, what are wave numbers? So, wave numbers, we remember from general chemistry, and we also reviewed this equation last time, is that delta E is equal to Planck's constant times C divided by lambda. And lambda, of course, is the wavelength. Now, wave numbers are defined as 10 to the fourth divided by lambda. And so if we substitute, we can solve this for lambda. Lambda is equal to 10 to the fourth over the wave numbers. We can substitute this into this equation, and we get that delta E is equal to hc over 10 to the fourth. So this piece is all constant, times the wave numbers. And so the important piece here, for the moment, is that the energy required is directly proportional to the wave numbers. All right, now why does that matter for what we're doing? Well, before we talk about that, let's get into some other details that are going to help us. And the first is that the energy we're looking at here is pretty low. Because we're not breaking bonds when we look at infrared. What we're doing is either stretching a bond so the energy we're looking at is what we need in order to stretch or bend a bond. And compared to a lot of other things, that energy value is pretty low. So how low is it? Well, you could plug these values in and actually do the calculations, but I've done those for you already. And what do we get when we do those calculations? Well, we find that one wave number calculates out to about 2.86 calories per mole. And if you think about most bonds, when we talk about bonds, we're typically talking about kilocalories. So 1 wave number is a very small amount of energy. Well, what about at the high end of our spectrum? If you go back and look at that spectrum, you'll see that the high end is about 4,000 wave numbers. Even that only calculates to about 11.4 kcals per mole. How strong is a bond? Well, a carbon-hydrogen bond, for example, is approximately 104 kcals per mole. So we're not anywhere near enough energy to break a bond when we're dealing with IR and the energy involved in the infrared. But what's happening in one of these cases when an IR spectrum is being taken? Well, what's going on is that the bond itself is being stretched or bent in different ways that can be detected by what we're doing in the infrared spectrometer. And those vibrations and stretching and bending vibrations are what give us peaks. So what does this process look like? Well, in this video, we'll watch this for a couple minutes. We see that there are 6 examples of different types of vibrations that can take place. There's symmetric and asymmetric stretching. Those are what we are normally focusing on more. Most of our functional group peaks are from these stretching vibrations. And then there's the bending vibrations, the rocking, wagging, twisting, and scissoring. But this short video will show you what these are actually doing at the atomic level. Alright, so there's also another good illustration of this if you'd like to see another example of what these look like, is to go to the link that I've just pasted here into these PowerPoint slides, and you'll see some nice simple animations of this as well. But for right now, sort of our take-home message from this is that stronger bonds I would think logically require more energy. And so because of that direct proportionality that we saw a few slides ago, that delta E is equal to hc over 10 to the 4th times the wave numbers, stronger bonds require more energy and are found at higher wave numbers. Now, another way that we can approximate what's going on here is to think about Hooke's law. So for those of you who have taken physics, you may recall this. This is based on the harmonic oscillator. And that's the last time I'll ever mention those words in this class. But it's really, I want us to see the equation that's involved here because it helps us to see how different things affect the wave numbers. So if we think of our two masses as point masses that are connected, it can be shown that the wave numbers are equal to 1 over 2 pi c times the square root of F. F is a force constant, and is, for our purposes here, really just a measure of how strong the bond is. So if the force constant is high, if the bond is strong, then that means we have a high force constant. So we take the force constant times the sum of the two masses, m1 plus m2, divided by the product of the two masses, m1 times m2. And so this leads us to two conclusions, one of which we were already aware of, but we can see it directly here. So if the force constant is a direct measure of how strong the bond is, then the stronger the force constant is, the stronger the bond is, the higher the force constant is, and the higher the force constant, the higher the wave numbers. So stronger bond, higher wave numbers. We can also see that the wave numbers are dependent on the mass, and given that we're multiplying the masses in the denominator, as we get a higher mass, that leads us to lower wave numbers. So this is our introduction to IR. Where we're going to go with this next is to start talking about what we can actually see in an IR spectrum. And to do that, we're going to look at a lot of actual spectra, and that's where I'll continue in the next video.